Welcome to today's paper reading. Today's paper is titled, On Calibration of Object Detectors, Pitfalls, Evaluation and Baselines. This paper was published on AR14 by Selim, Kuzucu and colleagues from 5AI Ltd. The abstract highlights the importance of calibration in object detectors, which is essential for reliable usage. Recent approaches include designing new loss functions and using post-hoc temperature scaling to calibrate detectors. However, these methods have notable drawbacks in their evaluation frameworks and metrics, leading to incorrect conclusions. To address these issues, the authors propose a new principled evaluation framework and efficient post-hoc calibration methods like Platt scaling and isotonic regression. Their experiments show that these post-hoc methods are more effective than recent train-time calibration techniques, as demonstrated by superior performance on the COCO dataset. Calibration is crucial for models in safety-critical applications, such as autonomous driving and medical imaging, as it allows for the characterization of error behavior, making the model more reliable. However, evaluating the calibration of object detectors is challenging due to varying detection sets and the need to choose an operating threshold that influences performance. Our proposed framework addresses these challenges by implementing model-dependent threshold selection, using fine-grained confidence scores that reflect localization quality, and ensuring datasets are properly designed for evaluation. Figure 1 illustrates the performance of different object detectors across varying operating confidence thresholds on the COCO Minitus dataset. The detectors evaluated include Faster RCNN, orange, RSRCNN, green, ATSS, purple, PA, red, and DDTR, blue. The measures presented are such that lower values are better for all except average precision AP. The figure highlights the difficulty in identifying an optimal operating threshold and comparing detectors effectively, particularly when relying on the common evaluation framework that combines detection expected calibration error, D-ECCV, for calibration and AP for accuracy. To address these challenges, the figure suggests using D-ECCV 0 and localization recall precision error, LRP, as alternative evaluation measures. Table 1 outlines the fundamental principles for evaluating the joint performance of object detectors in terms of accuracy and calibration. The principles include model-dependent threshold selection, fine-grained confidence scores, and properly designed datasets. The table then assesses whether existing evaluation approaches, such as D-ECCV style, D-ECCV style, C style, and the proposed method, adhere to these principles. It highlights that while some approaches like D-ECCV style and the proposed method meet certain criteria, others like D-ECCV style and C style fail to comply with multiple principles, indicating potential drawbacks in their evaluation methodologies. In object detection, the output consists of a bounding box by, a class label CI, and a confidence score pi for each detected object. During evaluation, metrics like AP, area under precision recall curve, and LRP, which combines true positives, and false negatives, are used. Additionally, D-ECCV measures the calibration error by discretizing the confidence space into bins. Calibration methods in object detection can be categorized into training time approaches and post-hoc methods, with TS and IR being notable examples. The D-ECCV style evaluation method has several critical issues. Firstly, it relies on a model-dependent threshold selection, using the top 100 detections and a threshold of 0.30, which creates inconsistency in detection sets. Secondly, the fine-grained confidence scores used in this evaluation do not provide information about localization quality, as they are typically binary targets. Lastly, the use of a domain-shifted validation set can significantly impact the performance of post-hoc calibrators, emphasizing the importance of proper dataset design. Figure 2 presents a comparison of various calibration methods, specifically focusing on the detection error calibration error, D-ECCV, metric, as applied to the COCO mini-test dataset using the DDTR model. The figure highlights the performance of post-hoc calibrators, namely temperature scaling, TS, and isotonic regression, IR, which were derived from a subset of the Objects 365 dataset following the D-ECCV style evaluation protocol. This comparison is crucial for understanding the effectiveness of different calibration techniques in aligning the confidence scores of object detection models with their actual performance on a given dataset. Figure 3 provides a visual comparison of various calibration errors in object detection. Panel A shows uncalibrated detections from DDTR, where the left detection has an IOU of 0.74 and the right one has an IOU of 0.48. Panel B illustrates calibrated detections using D-ECCV and D-ECCE with a threshold tau equals 0.50, along with COCO-style D-ECCE, D-ECCE, which does not have a global minimum as indicated. Panel C demonstrates calibrated detections where confidence matches IOU for D-ECCE 0 and D-ECCE 0. Panels D-F depict calibration errors for different detection types, with D-ECCE 0 behaving similarly to D-ECCE 0, thus omitted for clarity. Detailed analyses are provided in Appendix B. Table 2 illustrates the impact of employing a domain-shifted validation set on the IR calibrator. The results are presented on the COCO-Minidis dataset. For uncalibrated DDTR and the training time calibration method CalDTR, the validation set is marked as not applicable. The table highlights that the IR calibrator, when obtained from the in-domain validation set, significantly outperforms the one derived from the domain-shifted set. Specifically, it shows an improvement of approximately 11 D-ECCE over the domain-shifted IR calibrator and a 7.4 D-ECCE enhancement compared to the state-of-the-art CalDTR. This underscores the critical role of dataset design in achieving proper calibration performance. Table 3 highlights the impact of adopting COCO training settings on DDTR when trained on the Cityscapes dataset. The training modifications include using larger images and extending the training duration. These adjustments result in DDTR performing slightly better than CalDTR in terms of both accuracy and calibration. The tailored training approach for Cityscapes, which has a smaller dataset size and higher resolution images, demonstrates the importance of adapting training settings to specific dataset characteristics. Calibration in object detection refers to the alignment of a model's accuracy and confidence. For an object detector to be calibrated, its confidence should reflect both its classification and localization accuracy. The common calibration measure, D-ECCE, only considers the precision of a detector and ignores its localization performance. D-ECCE, an alternative to D-ECCE, enforces confidence scores to represent the product of precision and average IOU of true positives, TPs. However, D-ECCE only considers ES of TPs and ignores localization qualities of detections if their IOU is less than the TP validation threshold tau. To address this, we propose using tau equals 0, which simplifies the calibration criterion of D-ECCE to align the confidence score with the IOU. Additionally, we introduce D-ECCE 0, which uses an adaptive binning approach to capture model behavior precisely by ensuring each bin has only one detection, resulting in a measure that corresponds to the mean absolute error between the confidence and the IOU. Table 4 provides an overview of the datasets used for evaluating object detection and instance segmentation methods. The COCO dataset includes 80 object classes of varying nature, making it a comprehensive benchmark for common objects. It contains both bounding box and instance mask annotations, which are utilized for both object detection and instance segmentation tasks. The Cityscapes dataset, on the other hand, focuses on autonomous driving scenes and consists of 8 classes. It is commonly used in contemporary training time calibration works for object detection. Lastly, the LVIS dataset is a challenging long-tailed dataset with over 1,000 object classes and rich annotations for both object detection and instance segmentation tasks. Each dataset is described in terms of its training set, validation and ID test sets, and domain-shifted test sets, providing a detailed understanding of the data used in evaluations. In this section, we present the experimental evaluation of our proposed methods, Platt scaling, PS, and isotonic regression, IR, against state-of-the-art, SOTA, calibration methods. Our results demonstrate that PS and IR significantly outperform SOTA CalDTR, with improvements in D-ECCE and D-ECCE metrics. These improvements are not only observed on the COCO dataset but also generalized to the Cityscapes dataset. In the common object setting, IR and PS maintain the top two positions across various test subsets, showing significant gains on the ID set and COCO-C. For the challenging test set with natural shift, IR and PS improve LICE0 but show slightly worse performance in terms of LICE0, which is an expected drawback of post-hoc approaches under large domain shifts. In the autonomous driving setting, our approaches consistently outperform all training time calibration approaches, with very significant gains in LICE0 compared to SOTA CalDTR, further highlighting the efficacy of our post-hoc approaches. Table 5 presents a comparison of state-of-the-art SOTA methods in terms of various evaluation measures on the COCO dataset. The localization recall precision (LRP) is reported using optimal thresholds obtained on the validation set, while average precision (AP) is reported for the top 100 detections. The threshold tau is set at 0.50, and all measures are considered lower better, except for AP, which is higher better. The table highlights the best and second best methods in bold and underlined formats respectively. Post-hoc calibration methods, specifically Platt scaling, PS, and isotonic regression, IR, are shown to outperform existing training time methods significantly. These methods are particularly effective when the calibration objective aligns with the evaluation measure, as indicated by the results on the COCO Minitest. The table also notes that previous approaches optimized for D-ECCV thresholds from 0.30 see improvements with PS, reducing D-ECCV by 7.8. Overall, the post-hoc calibrators demonstrate superior performance when the calibration objective is well aligned with the measure being evaluated. Table 6 presents a comparison of state-of-the-art SOTA calibration methods on common objects using our proposed evaluation framework. The table highlights that our post-hoc calibrators, isotonic regression, IR, and Platt scaling, PS, share the top two entries on almost all test subsets by preserving the accuracy, LRP, of DDTR. Specifically, our gains on the ID set and COCO-C are significant, where IR outperforms CalDTR by around 3 to 4 LICE0 and 1.0 to 1.5 LICE0. For the OBJ45K set, which is a challenging test set with natural shift, IR and PS improve LICE0 but performs slightly worse in terms of LICE0. This is an expected drawback of post-hoc approaches when the domain shift is large, as they are trained only with the ID validation set. The table also indicates that IR and PS are the best and second best methods in terms of calibration, respectively. Table 7 presents a comprehensive comparison of state-of-the-art SOTA methods in the context of autonomous driving, utilizing our proposed evaluation framework. The table highlights the performance gains of isotonic regression, IR, over the best existing approach, CalDTR, demonstrating improvements ranging from 5.0 to 8.5 in LICE0. This consistent outperformance across various settings underscores the efficacy of IR in enhancing calibration metrics. Notably, IR not only outperforms CalDTR but also maintains superiority over other training time calibration methods, indicating its robustness and effectiveness in real-world autonomous driving scenarios. Table 8 compares the performance of temperature scaling, TS, with different design choices, including our proposed Platt scaling, PS, and isotonic regression, IR. The table highlights that using a domain-shifted validation set, denoted by, significantly degrades the accuracy of TS, as indicated by the red font. This is because the operating thresholds obtained on these validation sets do not generalize well to the in-domain ID set. The table further shows that our PS outperforms the TS baseline obtained on the ID validation set by approximately 3 LICE0 on the COCO dataset and 11.4 LICE0 on Cityscapes. Additionally, IR performs at least as well as PS, indicating its effectiveness as a calibration method. The table also includes ablations on TS, showing that thresholding the detections and using class-wise calibrators generally improve the performance of TS. Notably, the use of a bias term in PS leads to a more significant gain in performance. Overall, the results underscore the efficacy of our proposed PS and IR methods in improving calibration performance across different datasets and settings. Table 9 presents the results of calibrating and evaluating different object detectors using the common object setting on the COCO Minidist dataset. The table highlights that isotonic regression, IR, consistently performs better than Platt scaling, PS, in calibrating the detectors. Specifically, IR significantly decreases the range of ECCV from 10.6 to 34.4 down to 6.7 to 8.9, preserving accuracy. Among the detectors, MOCE performs the best in terms of accuracy with 40.7 LRP, while CodeETR achieves the best calibration with 6.7 ECCV and 19.3 ECCV. This suggests that future work should aim to surpass these results, particularly in improving calibration techniques for object detection. Table 10 presents the results of calibrating and evaluating instance segmentation methods on the long-tailed objects setting using the LVIS dataset. The results are reported on the LVIS Minidist set, with additional details available in Appendix D for the domain-shifted LVIS Minidist C. The table highlights that isotonic regression, IR, significantly improves calibration, reducing ECCV by up to 9 points and ECCV by 2.8 points. This demonstrates that IR remains a strong baseline for this challenging setting with around 1K classes. The table also emphasizes the need for further research on calibration under long-tailed data, as ECCV and ECCV are greater compared to COCO and Cityscape's Minidist, suggesting the complexity of the task. Figure 4 presents the reliability diagrams of the overconfident UpDTR detector, illustrating the impact of calibration using IR. The uncalibrated detector shows a high ECCV of 34.4%, indicating significant overconfidence. After calibration with IR, the ECCV is reduced to 8.2%, demonstrating a substantial improvement in reliability while maintaining accuracy. This improvement makes IR a robust calibration method for detectors like UpDTR. The paper highlights the critical role of evaluation tools and baselines in the progress of a field. It points out significant drawbacks in existing evaluation tools for calibration and baseline post-hoc calibrators for object detectors. To address these issues, the authors introduced a new evaluation framework that includes baseline post-hoc calibrators specifically designed for object detection. Experimental results suggest that, when properly evaluated and designed, these post-hoc calibrators significantly outperform all existing training time calibrators. This finding underscores the need for further research to develop better calibration techniques for object detection. The authors believe that their evaluation framework will be an essential component in this future research. Thank you for watching.